My name is Dima Kotik. I'm an application security engineer at Security Journey. We provide security training by developers for developers. Today we'll talk about the options pattern and how it is so important for solving OWASP Top 10 number 6, security misconfiguration. It doesn't matter how well your program is set up with access control and analysis tools and all the additional security features if it is misconfigured in production. It will be spotted and attacked, and they do get attacked, as you can see, top 10, number 6. The other problem is that two pieces of advice given to help with this are not super helpful. One is stop misconfiguring services. This is difficult to do as our services and applications are sophisticated, even more so every year. The other one is to use an analysis tool, a static or dynamic analysis tool. But those can detect problems that they have seen before. And the cost of discovery is far greater to take into account as a preventative measure. The question is, can we do something on the engineering side to make our applications resilient against security misconfiguration? And yes, we can. Enter the options pattern. The options pattern is a flexible object provisioning strategy using a list of independent object modifiers. Those are typically functions. To prepare your object, you apply consecutively, one after another, a modification to one or two of each of its parameters. Using an example using Golang, let's define a type called option. It will take a pointer to the object we're trying to configure and return an error. As an example, using a simple option called with email associated with our bank account we're trying to configure, we will take an email string and return a closure. A closure will take the pointer to our bank account and validate, first of all, the email. We will return an error if something is wrong. In some languages, we may want to throw an error here. If everything went well, we will assign the validated email to our main object and return nothing. To use a list of options, we will use a constructor that accepts a list of options, and we will initialize a blank bank account and iterate through every option and apply each option to our bank account until an error occurs. And we will wrap that error as initialization error so that can be handled upstream. If an error does occur, we want to interrupt the execution to indicate an insecure or possibly insecure state. Notice that our validation code is not going to live on our constructor. We will move all of it into the options. The constructor will simply check if mandatory parameters are set towards the end and return our configured object. How does this help? Well, first of all, it helps us guard against invalid or insecure state. Each option can check each parameter and include logic, flexible logic, to make sure that it's within the right range, within the right expected value, it's not a nil, etc. It also helps us protect against failures originating in parameters. Parameters can be sophisticated, they can pass behaviors. What about caches and drivers and networking layers? Those are sophisticated parameters. How do you know if they were configured securely? How do you know that their settings do not conflict with your object? Using an option pattern gives you an opportunity to check. When you take the parameter, validate it thoroughly all the way through inside the option. And lastly, it helps us protect against conflicting parameters. Two parameters on their own may not make your program insecure, but interactions between them can easily do so. One can undermine the other and put the application into an insecure state. Let's look at a more realistic example. Let's suppose we're writing an asset encoder for an IoT device, a simple one that will use a block size and a buffer size, a buffer limit. Immediately, we know that there's three things to keep in mind. First of all, the limit has to be greater than 0 and greater than size. The limit has to be a multiple of this size because we don't want to end up with an underflowing or overflowing buffer in the end. Who knows what that will lead to? And lastly, we know there's perhaps protocol constraints that introduce additional limits. So, mind you, in low-level languages, each one of those is potentially a security vulnerability because we're talking about memory management. But even in a memory-safe language like Go, this can still create conditions that will unsettle the program. So we want to anticipate those conditions, threat model those conditions, and check them inside the option. And then only assign our variables to block size and memory limit after they were both checked. Notice that we're combining the two under one option. This is what we call self-documenting code. The consumer of our API will know that those two have a relationship with them that can be significant for security. To sum up, there's 4 key takeaways. If something can be misused, it will be misused. Be secure by default, and that means that weekend services should not even start, and the options pattern can help you ensure that. Second, the option pattern guards against misconfiguration, invalid initialization states, and other states that lead to vulnerabilities. Third, the options pattern is convenient and automated for testing. You can see we isolated all that logic into individual units. With multiple parameters, it makes it quite easy to make sure that your tests back up the security that you claim. And finally, I hope this talk inspires you to implement the options pattern in your next major version release to bolster security with a boost of code reliability, readability, and resilience. Thank you.